In this lesson, we are going to carry on looking at relations, and in particular, we're going to look at the difference between linear relations and nonlinear relations. So, the idea is when I talk about a relation being linear, what I am indicating is that if I look at the graph of it, it's going to be a straight line. So in math, linear means it's a straight line, whereas nonlinear simply means that it's going to be a curve. That's the easiest way to picture it in your minds, all right? There's actually three different ways of determining if something's linear or nonlinear, though. And I already talked about the first way. If we have a graph, or we can picture the graph of a relationship, then we can immediately tell if it's linear or nonlinear by seeing whether it's straight or a curve. All right, so what about the other ways, though? What if we have a table of values? Okay? We can still tell if something is linear or nonlinear from the table of values. It just takes a bit more work. What we do is we look at the difference between dependent variables. Remember in the last lesson, we defined independent variables as the ones that were on the left side of a table of values. They're the ones that we pick. And then the other variable was the dependent variable, and that was on the right side of the table of values. And we calculate those based on whatever the relationship is. So we're looking at the values on the right side of the table, and we're looking to see the differences between sequential variables. So going from one to the next and just seeing how much they're going up or down by. We want to see if they're increasing or decreasing at a constant rate, okay? So if the differences are constant, in other words, going up or down by the same amount each time, the relation is linear. That'll become a lot clearer when I do an example. I guess the flip side of that, though, is that if the differences are not constant, if they don't go up or down by the same amount, then the relation is not going to be linear. So it would be a curve if I were to graph it. Anyway, I'll do an example of that in a minute. The last thing, though, we can do is we can look at the equation. It's actually possible just to look at an equation and tell if a relation is going to be a straight line or not. And the way we do that is we look at the exponent on the independent variable. If that exponent is 1, the number 1, then the relation is linear. For example, y equals 3x plus 2. That's a relationship, right? X is the independent variable because it is the one that we're doing things to. Remember, y is the dependent variable. It's the one that's by itself. It's the one we get by doing things to the independent variable. The variable, sorry, the exponent on the independent variable is 1. There's no variable exponent written there at all, but we've learned that if there's no exponent written on a variable, it's assumed to be 1. So there's assumed to be a 1 there, and therefore this is a linear relation. If the exponent is anything else, then it's nonlinear. So let's just look through a few examples and see how this works. State whether the following are linear or nonlinear and how you know. Okay, so again, if we have a graph, pretty straightforward. The first one, the one on the left, is a straight line. It's linear. And the one on the right is not a straight line, it's a curve. That makes it nonlinear. So super easy if we actually have the graph to look at. Here's where it's a little trickier for the table of values. So again, on the left, you can see we got x. That's our independent variable. And y on the right is our dependent variable. And so what I do is I look at the differences in the dependent variables. So if I start at 7, and then I go to 9, just imagine that part. So I'm starting at 7, and I'm going to 9. What's happening? Well, I'm going up by 2, right? If I'm going up by 2, that's my difference. The difference between 9 and 7 is 2, positive 2. And then if I go from 9 to 11, I'm going up by 2 again. And then from 11 to 13, up by 2 one more time. So if you go back and look at this definition, if the differences are constant, as in all the same, the relation is linear. So these are constant. That's what I mean by constant, that they're all the same. Therefore, this is a linear relation. If we do the same thing in this next example, again, I'm only looking at the y values. So I go from 0 to 1, well, that's going up by 1. If I go from 1 to 4, now I'm going up by 3. And then if I go from 4 to 9, I'm going up by 5. These are not constant first differences. So if they're not constant, it's nonlinear. Something I should point out that I haven't mentioned yet is if you look at, this only works if the x values are going up at a constant rate already. So if I go back to my first one on the left, I start at 0, and then it's 1, and then it's 2, and then it's 3. Those are going up at a constant rate. So that has to be the case. So I couldn't go, say, 0, 1, 5, 23, or something like that on my x's. I can only check the y values if these are constant to start with. Okay? Same with these ones, 0, 1, 2, 3. They're going up at a constant rate. So it's a prerequisite that our x value, our independent value, must be going up at a constant rate. Then we check the dependent variables. All right, and then the last one, we want to look at our variables in our equations. And I guess what I said above was that if the exponent on the independent variable is 1, the relation is linear. I should actually amend that, because seeing those examples remind me that even though we'll usually see it in this case, we actually want the exponent on all variables to be equal to 1, both the variables. So both the independent and the dependent variable. So let me just squeeze that in. Both the dependent and the independent variable is 1. It's a bit of a cheat there, but that's more accurate to say it like that. So look at the equations. If the highest exponent is 1, or if the exponent is always 1, and again, 1 would be indicated if there's no exponent there, then it's going to be linear. So for this one, I can tell right away it's linear because the exponent on x is assumed to be 1. The exponent on y is also assumed to be 1, and that's what I'm looking for. In this example over here, we've got an exponent of 2 on the x, we've got an exponent of 4 on the y. Either one of those by themselves is enough to make it nonlinear. Putting them both in there definitely confirms that it's nonlinear. So that one was a fairly short lesson. Again, now you need to do the homework that goes with it. Let's just take a quick look at that to make sure that I don't have anything to point out here. Just looking through these questions, I think that that's pretty straightforward as far as today's lesson goes anyway. So give this a try, please.